Good afternoon, everyone. Can you hear me okay? Well, as some of you may or may not already know, the U.S. Department of Defense is currently interested in the development of a wearable health monitoring system that can continuously collect information on the heart and the lungs of the wearer while running solely on energy harvested from human motion. I'm Jeremy Marshall, and the object of today's discussion is to demonstrate the feasibility of a self-powered biosensor system measuring heart and respiratory rates. Here are the highlights of our discussion. The background portion will go over some key concepts that are closely related to the work that's being done here. After, we'll go over a few of the previous engineering approaches that have been inspired by the idea of harvesting energy from human motion. Next, we'll discuss a new approach, of which will serve two purposes. One, it will be more efficient when it comes to harvesting energy from human motion. And two, it will serve as the energy harvesting method for the biosensor system that we're looking to create. Afterward, we'll go into some details about our biosensor system as a whole. And then, before we conclude, there will be some final remarks about the current stages of this research project. Now, there are four key concepts that I need to convey before we dive into the details of our discussion. First, when I use the term biosensor systems, I'm referring to a wearable unit mainly composed of sensors, of course, to measure your heart and respiratory rate, and a power source. Now, for this particular project, that power source will be energy that's gathered from human motion. Next, it is expected that these biosensor systems that we make will be used for our soldiers and armed forces. Next is the concept of piezoelectrics. It's the idea of creating electricity through bending what's called a piezoelectric element. Now, a piezoelectric element can come in many different shapes and sizes. It can be a long, thin rectangle like what we see right here, or even a short circle like here. But the bottom line is this: when a piezoelectric element is bent, electricity is created within that element. It travels through the connecting wires into whatever object that the piezoelectric element is linked to. Lastly, we have a set of design requirements that we must consider when we're doing our review of those previous engineering approaches to human energy harvesting. First is performance. Each of these devices that are supposed to harvest energy from human motion must not have a negative performance on the wearer, or a negative effect on the performance of the wearer. It cannot be too big, too heavy, too uncomfortable. You'll see what I mean later on. Next is electrical yield. Each of these devices must produce a usable amount of electricity. If you're wearing something that's supposed to be making electricity to power some sensors, but it doesn't produce enough electricity to power the sensors, then what's the point of wearing it, right? Next, continuous operation. Each of these energy harvesting devices must be able to collect electricity continuously. You'll see what I mean later on. Now, our first approach is the energy harvesting chest belt. It gathers energy from breathing through the use of an electromagnetic generator and an elastic band. The generator right here is a little larger than a 9-volt battery. Here you can see that band used in conjunction with that generator. As the wearer breathes in and out, that band expands and contracts. That expansion and contraction of that band is what engages gears within that electromagnetic generator, which in turn creates electricity. Now let's look at our design requirements. First, when it comes to performance, we can see that this is an excellent device because its unintrusive design has no effect at all on the performance of the wearer. It's simply an elastic band on your chest. When it comes to electric yield, however, it produces a peak power of only 15 milliwatts. 15 milliwatts, which is a little bit more than what you need to power a common household laser pointer. And that's not very useful, unfortunately. However, when it comes to continuous operation, this device performs very well. It's a chest belt that gathers energy from respiratory motion. So as long as the wearer is breathing, this thing will be collecting electricity, right? So the wearer could be walking, could be jumping, could be running, could be doing a presentation. As long as the wearer is breathing, this device will be collecting electricity. It can operate continuously. Now our next device is the energy harvesting backpack. It uses the idea of humans walking to create electricity. You see, when we walk, we're like inverted pendulums. We take a step, we pivot about that foot, and our center of gravity rises up, comes back down as we continue to move forward. Objects in our body have a tendency to want to slide up and down, but typically they can't because they're tethered to us. If I were to wear a backpack and I were to walk, it wouldn't slide up and down on my back because it's tethered to me. But the unique thing about this energy-absorbing backpack is that it has a sliding load compartment. I'm not kidding. It has a sliding load compartment. In that load compartment, you can put whatever you carry as a soldier, whether it's your ammunition, your water, your food, whatever. Carry all of your stuff in that load compartment, and as you take a step, that load compartment is allowed to slide up and down because it's mounted on this frame here that has a sliding mechanism inside. The sliding load compartment has a shaft with teeth on it. As the load compartment slides up and down, the teeth on that shaft engage a gear on the electromagnetic generator, which in turn creates electricity, thus the energy harvesting backpack. Now let's look at our design requirements. For performance, this thing doesn't do so high. In order to produce its maximum electrical output, the wearer must carry a total of 80 pounds in that load compartment. You don't have to be an expert to know that that's nothing good for your performance. 80 pounds to your back, come on. When it comes to usable electrical yield, however, it does pretty well. It produces a total of 7.37 watts, which has been noted to power a cell phone and even a GPS receiver, which is definitely good. However, it does not operate continuously. We're talking about only collecting energy when you're walking, not when you're standing, sitting, or lying down. It does not operate continuously. Next, we have energy harvesting shoe. It's a very simple design, the simplest design I have here. All it is an externally mounted generator on the shoe of the wearer in conjunction with a lever that's placed beneath the heel. As the wearer walks, they compress the heel engages the electromagnetic generator, and that creates electricity. Pretty simple, right? Yeah. Now let's look at our design requirements. When it comes to performance, this too is not doing very well. That lever underneath the heel has been noted to be a huge hindrance when the wearer is walking. Great interference with the gait of the walker. It's very difficult for you to press that heel when you're walking. It's like walking with high heels, except they kind of compress a little bit. That's horrible things for your performance, especially if you're a soldier. When it comes to electrical yield, the object this device performs okay. It produces a total of 1 watt of electricity, which is enough to power a flashlight. However, it does not operate continuously. We're talking about only collecting energy when the wearer is again walking. Not while the wearer is standing or sitting down. You have to be walking. Now, a lot of these approaches have some complications. Not to worry, good citizens, for there is a solution. Dr. Agamemnon Crassidis, my mentor here at RIT, has joined forces with Dr. Robert Andosky, the CEO and founder of Microgen Systems, to come up with a new approach to harvesting energy for human motion. And the key to that approach is the MEMS energy harvester made by Microgen Systems. It's a piezoelectric energy harvester that gathers energy from vibrational motion. If this were the energy harvester right here, all I have to do is shake it a little bit, and it would be collecting energy and turning that into electricity because the piezoelectric elements on the inside are bending and flexing, and that's what's creating electricity. Here's an example of one of those MEMS energy harvesters. This is an older model, but they're about the same size, and you can actually see piezoelectric cantilever on the inside of that energy harvester. We're considering taking these energy harvesters and strategically placing them on different parts of our soldiers. We're talking about perhaps putting them into the shoes of our soldiers to gather energy while the soldiers are walking. We're also considering making an energy harvesting chest belt, similar to what I described earlier, except the main difference is that the energy harvesting component of that chest belt will be the MEMS energy harvester. Additionally, we're considering taking some of those energy harvesters and putting them on the firearms to gather energy from recoil during the discharge of ammunition. A lot of energy is wasted. We could use that energy. Now I discussed the power source of our biosensor system. I'm going to go into the sensors. To measure heart rate, we would use a small pressure sensor that will be placed on the wrist of the wearer, right where your pulse can be felt. This is a small, highly sensitive pressure sensor. And easily measure the heart rate. Interestingly enough, to measure respiratory motion, you can also use the both limbs energy harvester. Because of its unique design, not only can it gather energy from motion, but it can also be used to monitor motion. So while the wearer is breathing, the wearer of the chest belt is breathing in and out, it will collect energy from that motion. It can also be used to monitor that motion, thus monitoring respiratory rate. And of course, our power supply would be energy that's harvested through motion. Everything that I've discussed here today has been compiled as part of a research proposal that's been submitted to the Department of Defense in response to one of their 3-phase research programs. Our current hope is to have our proposal accepted so that we can move on to the next phase of development, put together a wearable prototype of our self-powered biosensor system. I am Chair Marshall.